Hi everyone, I'm Loo Kai Xen, and my FYP topic is damage detection of carbon fiber composite cantilever beam using model analysis of structural vibration. For my introduction, first the problem statement. Carbon fiber is durable, but it also fails or breaks devastatingly if occur. Therefore, damage monitoring is needed to make sure good operating condition of the carbon fiber all the time. Destructive testing, however, will damage or alter the structure and cause the carbon fiber to be no longer compatible for service. For the objective of this project, firstly, this project aims to develop, optimize, and verify carbon fiber cantilever beam model in ANSYS and through experiment. This project also aims to predict changes in natural frequency of the beam based on damage location, damage severity, and number of damage. For the methodology of this project will start with literature review and then proceed to the preparation of carbon fiber specimen. And then we'll carry out the experiment 1, tensile test of the carbon fiber tensile specimen to obtain the specification of the specimen. Then we'll input this data into the ANSYS to develop ANSYS simulation and obtain simulation natural frequency. Then we'll proceed to experiment 2, random vibration spectral test to obtain experimental natural frequency through model analysis. And then we will carry out validation and verification of the simulation and experiment natural frequency. And if they are validated, we will proceed to variables planning. And we will do prediction of natural frequency for 3 cases of damage, which is damage location, damage severity, and number of damage. Then we will do discussion, which do analysis for the damage detection in the carbon fiber beam. Then we'll end our project. This experiment aims to determine the tensile strength, and it's based on ASTM standard. The tensile specimen design parameters is on the left and the actual specimen is on the right. This is a schematic diagram of the tensile testing machine. Next, we will proceed to carbon fiber composite beam detail. So as you can see, there are 2 dimensions here, the planned dimension and actual dimension. Planned dimension is the beam dimension sent to the manufacturing company to be manufactured, but the dimension of manufactured beam, actual beam is slightly different due to uncertainty of the manufacturing equipment. Therefore, for the experiment and simulation, we will use the carbon beam dimension based on actual dimension. This is the experiment setup for experiment 2, random vibration test of carbon fiber cantilever beam, and our source of vibration is using vibrator. This is a damage variable of the beam. As we can see, the beam is sectioned into 20 parts, and each part is applied damage on it based on location, severity, and number of damage. This is the result and discussion of the tensile test. We can obtain the tensile graph and obtain the Young modulus and Poisson ratio through these 2 formulas from the tensile graph. This is a random vibration test of the carbon fiber composite cantilever beam, and we can obtain the experiment natural frequency through the experiment, which have 4 peaks here. So this is the experimental natural frequency we obtain for the undamaged beam. This is the verification or validation of carbon fiber cantilever beam. So this is a simulation natural frequency that we obtain from the beam. So we will compare between the experimental and simulation natural frequency, and what I can conclude that is the percentage change is less than 5%, which means the data is verified. So this is the result based on damage variable. So this is the natural frequency for each damage location for mode 1, mode 2, mode 3, and mode 4. As we can see, if the beam is damaged, their natural frequency is lower than the undamaged one for all 4 modes. This is the result based on percentage change in natural frequency. What we can observe that when at element location 5, mode 1 is the most sensitive, element location 10, mode 2 is the most sensitive, element location 15, mode 3 is the most sensitive, and mode 4 is second most sensitive in all locations. Mode 1 natural frequency can be used to predict the damage location because when the damage is towards the fixed end, its changes in natural frequency is around 4.5%, and when it's at the middle of the beam, its changes is around 1%, and when the damage location is towards the free end of the beam, then the mode 1 natural frequency will detect less than 0.1% percentage change in the natural frequency. For the second variable, the damage severity, what we can observe that the percentage change in natural frequency increase with increased damage severity for all 4 modes. For the third variable, number of damage, what we can observe that for the mode 4 natural frequency, it increased linearly with the number of damage. Why it's like this? Because based on the damage location graph, we can observe that mode 4 natural frequency is second most sensitive in detect damage, means that fourth mode is more stable compared to other modes. So that in this number of damage graph, it will obtain a linear line. Unlike other modes, it did not obtain linear line based on number of damage. For the societal health and safety impact, this project can predict potential damage in beam. It is useful to in planning maintenance, boosting product quality, and prevent unscheduled downtime. It also prevents workplace accidents and reduces hazards. It can be done by real-time reaction to the change of health condition of the beam. It reduces operators' health risk and as it supports remote condition monitoring. As conclusion, damage detection via modal analysis is proved and verified. Model of carbon fiber cantilever beam is developed and verified in NCs with material defined from tensor tests. The percentage change difference between experimental and simulation natural frequency is less than 5%. The first, second, third mode is more sensitive at element location 5, 10, and 50 respectively. Post mode natural frequency reduced with increasing damage distance from the free end to damage position, which means that first mode is more suitable to detect damage at different locations. Almost detect higher percentage change in natural frequency with larger damage severity. The percentage change in natural frequency for fourth mode only increased linearly with number of damage. The rest modes increase non-linearly. For the assessment on implication to society and environment, this method saves costs as it will not damage tested beam. It lowers safety risk and hazards to operators. It allows material to be reused, so we no need to refabricate it, and it is indirectly good for environment. Thank you.